And now what we are going to see? We are going to see that how to write the equations for the multiphase flow for all these conditions or all these flow regimes which we have learnt. Now, before going to that, the flow equations, I would first like to briefly revise some of the things which we have already studied maybe in the fluid mechanics, but to bring everyone at the same platform so that we can understand the equation in more detail, I will do some revision, and that revision is very critical, very necessary, because we are going to build up our equations based on that. Now, first thing we always discuss in the multiphase flow or in any flow is that two kind of measurement or two kind of the phenomenon or two kind of parameter, what we say is the Eulerian flow and Lagrangian flow, or Eulerian measurement and Lagrangian measurement. So, first what we are going to understand that what is Eulerian, what is Lagrangian. So, that we should be very clear whether we are writing the equation in the Eulerian frame of domain or we are writing in the Lagrangian frame of domain, whether we are doing the measurement in Eulerian frame of domain or we are doing the measurement in Lagrangian flow of domain. So, what we are going to do? We are going to discuss about the Lagrangian versus Eulerian. Now, what is Lagrangian and what is Eulerian? Now, if you might have studied about this many places at the discrete places in your mass transfer, in your fluid mechanics, and we have tried to derive the equations also. We will again revise it because this is very, very critical. Now, what we are going to see is the equations we are developing, the measurement techniques we will be developing, it will be either the Eulerian measurement or it will be the Lagrangian measurement. And we have to know, we should know how to interchange the Eulerian information to the Lagrangian information or the Lagrangian information to the Eulerian information, so that we can use the system or we can analyze the system in more detail. Now, to understand this, what is Eulerian, what is Lagrangian, let us assume a system in which a flow is taking place and the flow is changing with the position. Now, we can easily assume any diverging or converging section, and if the section will be diverging, definitely the area will change. If the area will change, my velocity is going to change. So, suppose a fluid is flowing here in a diverging section. So, what will happen? Suppose I am taking two places here, one is section 1 and another one is section 2. So, what will happen? Section 1 suppose has a velocity v1, section 2 has a velocity v2. Why it is going to happen? Because my area has changed. We know the equation of continuity that a1 v1 will be equal to a2 v2 if the flow is incompressible, or we can say that overall mass transfer rate is going to be the same. So, overall mass transfer is going to remain same. So, rho a1 v1 will be equal to rho a2 v2. If rho is same, rho will be cancelled out, a1 v1 will be equal to a2 v2. It means I can write v1 upon v2 is nothing but it will be equal to a2 upon a1. Okay. So, if your area will change, your velocity will also change. Now, it means if a2 is higher than the a1, then what will happen? The v1 will be higher than the v2. Okay. So, that is going to happen. Now, what we are going to see that if suppose I am interested in measuring the velocity at any of this point, okay. Say I am interested to measuring the velocity at point 1, at any point here in between. Okay. Now, what will happen? Suppose I have a probe which can measure the velocity, say pitot tube. I can place the pitot tube at this place, this point, and it will give me the velocity at this point. So, suppose I am putting a pitot tube here. I hope everyone knows what is pitot tube. So, I am putting a pitot tube around this point P, and if I put a pitot tube, I will measure the velocity at that point. Now, if I assume that the flow is steady state, it means what? The V is not a function of time. Okay. So, V will not change with the time. So, what will happen? You will measure certain velocity here. Now velocity at this point and velocity at this point is going to be different. Why? Because the area is keep on changing. Now what you are measuring here is the velocity at a fixed place. Okay, so that is called Eulerian velocity. So what you will measure, say pitot tube is giving a velocity Vp, which is the, I am saying a point velocity, the velocity at a point P. This Vp is nothing but is the Eulerian velocity. It means what? When we fix our frame of reference or when we fix our position or specify our location and measure something at that location is called Eulerian field, okay, or Eulerian measurement or Eulerian quantity. So here we are measuring the velocity. Now I have fixed my position, so that what we are going to see is that this velocity, how it is changing with the time. Now if with the time this flow is steady state, then dou v by dou t will be 0 and you will be measuring the same velocity throughout the domain or throughout the time you are doing the measurement. Okay. If it is not, if the flow is not steady state, then with the time you will see that how the velocity is changing at that location. So suppose if flow is not steady, okay, or is an unsteady state flow, then you will see at point P how the velocity is changing with the time. This is time. This is Vp for unsteady state flow. For a steady state flow, what you will see? You will see this is Vp, this is the time. You will see there is no change in the velocity, and this is for steady state. So these all are called Eulerian or Eulerian velocity. Or Eulerian velocity, where the position has been fixed. Okay. If I change the position, if I suppose now if I am measuring instead of position P, I am measuring putting a new pitot tube which is at a position S. Okay, I will see another velocity Vs with time. If the flow is steady state, this Vs will be there. It can be more than Vp, it can be lower than the Vp, it can be same to Vp depending upon the flow condition. Okay, whether the flow is laminar or flow is turbulent. We know if the flow will be laminar, then what you will see? You will see a parabolic profile. So definitely if you are measuring at the center, velocity will be higher. If you are measuring near the wall, velocity will be lower. If your flow profile is turbulent, then what will happen? That near the wall you will see a tilted profile where the velocity will not be the same, but at the central portion the velocity will almost be same everywhere. In that case, if the 2 point is between this flat region, your Vp and Vs will be the same. If you are a laminar flow, you are going to have a parabolic profile, Vp and Vs will be different. So what we will see? We will see that how the velocity is changing with the location. So if I change the location, the velocity is changed. For steady state, for unsteady state flow, the velocity can change even at the same location with the time. Okay. For steady state flow, the velocity at the same location with the time will be the same, but if you change the location, it may change. Okay. So these all are called Eulerian field or Eulerian measurement or Eulerian velocity. But the problem is our most of the conservation law, whether the conservation of mass, conservation of momentum, conservation of energy, conservation of angular momentum, all those equations are written in terms of the Lagrangian field. Okay. What do you mean by the Lagrangian domain? It means if I am measuring the velocity of a molecule. So what will happen if the flow is taking place in this system, then the Lagrangian system, if I am talking about, if I do to the same divergence section, say 1 section, section 2, if I am talking about a Lagrangian system, then what will happen? If Lagrangian means you are sitting on a molecule of a fluid element and you are seeing how the velocity of that fluid element is changing with the time. It means suppose there is a molecule of the fluid element, I am sitting on top of it. what will happen? I will see that though the flow is steady state, my velocity is changing with the time. Okay, please remember this, though the flow is steady state. Okay, and this is very critical. So, though the flow is steady state, the velocity will keep on changing with the time. If I am sitting on the molecule, why? Because the area is changing, my velocity is going to change, and this is called the Lagrangian velocity. So, what is happening? My domain is not fixed and domain is changing with the time, and because the domain is changing, my environment is also changing with the time, and that is the reason that I am seeing a different velocity field altogether. I am not measuring the velocity, I am not seeing the velocity at a fixed domain, I am changing the velocity with the time. It means what? What is changing? The velocity is changing with the time, and the location of the molecule is also changing. It means here if I am measuring the velocity, this velocity will be the function of x, y, z and time t. It means if I have to write in terms of the derivative, I will write it as dv by dt. It will be what? It will be dou v by dou x into dou x upon dou t, okay, because position is changing with the time, dou b by dou y into dou y upon dou t plus dou v upon dou z into dou z upon dou t plus dou v upon dou t. How this is changing? Velocity is changing with the time. Okay. So, if that is also happening. So, now this is called actually the substantial derivative or material derivative, which is being widely used to understand the Lagrangian velocity field. That what is the Lagrangian velocity? This dx by dt will be equal to what? It will be the velocity if v is a vector, we know that, and has a 3 component vx, vy, vz. Then what will we can write it as a vx dou v upon dou x plus vy dou v upon dou y plus vz dou v upon dou z plus dou v upon dou t, where vx, vy and vz, v is nothing but is the velocity of the fluid element. Okay. When it is velocity of the fluid element, this dv by dt will be equal to the substantial derivative or the material derivative, in which this is what is called the Eulerian part, where we are seeing that how velocity is changing with the position and position is changing with the time in all these three, and how the velocity is also changing with the time. So, this part, if suppose you are doing the Eulerian measurement, if I am measuring the pitot tube, what I am measuring is this part, that how my velocity is changing with the time. If I put a pitot tube at a particular location, I am not changing the position here in this part. So, what is happening at a fixed location, I am seeing that how the particle velocity or how the fluid velocity is changing with the time. This is Eulerian velocity, and this is what is the Lagrangian velocity dv upon dt or the material derivative. And whatever the conservation equation we all see in terms of the substantial derivative, where the fluid element velocity comes into the picture, or the fluid velocity also comes into the picture, and that fluid velocity is being measured by how the fluid element is changing the position with the time. That is nothing but dx upon dt, which is nothing but the x velocity or x element of the velocity of the fluid, dy by dt or dou y by dt, which is the y element velocity of the fluid, dou z by dou t, which is the z element velocity of the fluid. Okay. So, that is the component. Similarly, any quantity, any parameter, you can write it in this form. So, I can say that do phi by dt, where phi is any quantity, it can be written as Vx dou phi by dou x plus Vy dou phi by dou y plus Vz dou phi by dou z plus dou phi by dou t, where this part is the Eulerian part. If you do the Eulerian measurement, you actually get only this. Okay. While writing the conservation equation, we see all this. So, what we need to learn, how to convert these two parameters and how to start the measurement in such a way that the Lagrangian information or the Eulerian information can be interchangeably used to understand about the system. And this whole equation, whatever in terms of the velocity we know, it is also called is Euler's acceleration equation, and you already have used in your fluid mechanics. Once you do the fluid mechanics, you derive the Navier-Stokes equation, you derive the Euler equation, and you make these equations like if the Euler acceleration is 0, how the equation will be converted, you do all sort of things. So, this is called Euler acceleration equation, in which this is shows that how the fluid element is being actually accelerating. So, this is what is the Lagrangian domain. What is the Eulerian domain? To summarize again, Eulerian domain means if your location is fixed, if your frame of reference is fixed and you are seeing the element of the fluid velocity or how the fluid velocity is changing in that element, in that fixed element is called Eulerian. So, what is happening? The fluid element is keep on changing, but the location is fixed. In the Lagrangian field, you are seeing that how the velocity of a fluid element is changing with the time. So, what is happening? Fluid element is fixed, but the location of the fluid element or the position of the fluid element is changing with the time. So, that is called, when the position of the fluid element changes with the time, is called Lagrangian measurement or Lagrangian velocity or Lagrangian quantity. When the element is fixed, observation element is fixed, and the fluid element in that observation circle or in that observation frame is keep on changing, and we see with the time how the quantity is changing in that fixed frame is called Eulerian measurement or Eulerian quantity. So, these are the two quantities which we need to understand. While doing most of the measurements, we measure in the Eulerian field domain like thermocouple, like pitot tube, like pressure gauge. What we do in thermocouple, we fix the thermocouple probe or that a particular location. So, we measure the temperature at that location. In case of pitot tube, you fix the probe at a particular location, you measure the velocity at that particular location, and what you measure is the Eulerian field. Most of our conservation equation is written in terms of the Lagrangian field, and that is why there is always a confusion between the Eulerian field measurement and Lagrangian field measurement, and I hope that now it will be little bit clarified. So, what we are going to do? We are now going to see that how to interchangeably use the equations, how to write the equation for the different multi-phase flow domain. Now, before that, what we are going to do? We are going to derive the equation, and that is very common equation is called Navier-Stokes equation and equation of conservation of mass. So, first we will see that how that equations are derived, so that once for all our basics are clear, and then by using that equation of momentum, we will try to see for different multi-phase flow regime how that the same equation can be modified. What we will try to do? We will try to fix our discussion in a single direction or in the one dimensional domain. You can convert that the same equation very easily in 2-dimensional and 3-dimensional domain. However, it will be numerically very challenging to get the solution. It's almost impossible to get an analytical solution for that. That's the reason that why we will be limiting our discussion for this course in a 1-dimensional domain, so that we can solve the problem, but one can easily extend the same discussion in 2-dimensional and 3-dimensional domain, but then you need numerical approaches, numerical methods or advanced computational methods or computational methods to solve those equations. Second thing what we are going to do, we will be limiting our discussion most of the time in the laminar flow regime, again for the sake of simplicity of the problem, so that we can understand the things, because turbulent will be completely different ball field, and if you go in the turbulent domain, your number of equations will be increased, your number of variables will be increased, and it will be very difficult to get an analytical solution for that. So, one is interested can do that. We will also try to look into the computational fluid dynamics method, how to solve the computationally the equations. We will briefly try to see towards that, but that is not the main focus of this course, but the main focus of this course is to write the equation in one-dimensional field, in one-dimensional domain for laminar flow equation. If you get the turbulent flow, do not be worried, it is exactly same, you are solving just few more equations to account the turbulent field. We will also try to have a small discussion on the turbulent field, but most of the time we will be limiting our discussion on the laminar flow field. So, these all I am classifying or clarifying, so that in future classes there will be no confusion and we will be keep on carrying our discussion on the laminar flow field. Okay. One dimensional laminar flow field, that is what we are going to cover. Turbulent flow field, if you read the paper, if you read the book, some books discuss about the turbulent flow field. Do not get confused, you can easily solve it. Only thing is the analytical solution will not be possible and you have to depend on the computational fluid dynamics method or advanced numerical approach methods to solve those problems. People use LES, people use DNS, people use some computational field in the finite volume method or finite difference method or computational approach to solve those equations, but we will limit ourselves in one-dimensional laminar flow. So, before going to the multi-phase flow, as I said that what we are going to see is how this Lagrangian field, Eulerian field is being kind of generated, how to write the equations properly and how the basic notion of how to develop and how to write first the general momentum equation or general mass conservation equation. So, for that the very basic thing which has been started is called Reynolds transport theorem. So, what we are going to do is theorem, also known as widely RTT. Okay. So, what Reynolds transport theorem says, suppose there is a fluid element which is moving, a fluid is flowing here, and if I take a small element here, a small say volume which is being there, and if suppose at time t equal to t plus delta t this volume is being swept, then what will happen, that you will see that it will move to a certain distance, and this is the same element I am saying that it has moved to the certain distance, and what will happen, you will see this is again moving. Now, what we can do, we can divide this element in three parts. One is the part 1, this is the part 2 which is actually the intercept, and this is the part 3. So, what is happening? A fluid element is there which is being placed in a moving fluid, and this will be swept with the velocity of the fluid, and because of that swept, some of the property will actually move outside of this control surface from the outer side, and some of the property from this control surface 1 will move to the inside of the control volume 2. So, there is a control volume and these are 2, 1 and 2 is the two control surfaces which is moving in, the property is moving in from control surface 1 and moving out from control surface 2. So, now if I have to write here, so if I see that, suppose if I am talking about any extensive property which is a property of mass and I am denoting it with a number n. So, this is extensive property. Okay. So, this can be energy mass, this can be momentum, this can be energy, and I am defining one more quantity eta which is in intensive property, or I will say the per unit mass quantity It means if I am defining n as a mass, then eta will be mass upon mass. It means the value will be equal to 1. If I am defining the momentum, it will be momentum per unit mass. Momentum is defined by mv divided by m. It means this will be cancelled out, it will be the velocity, and so on. If you define the energy and all, is all so on. So, if you define kinetic energy, it will be half mv square, it will be only half v square. So, in so on, you can define the quantity eta, which is intensive property per unit mass quantity, and is the extensive property, which is mass, energy, momentum, any quantity we are defining. So, we are defining a general equation. So, suppose a quantity n which is being swept and it is being from control surface 1, it is entering to the control volume 2 and then it is going out again through the control surface 3. So, what will happen at any time t, quantity n, suppose at time t the quantity n will be what? The quantity n will be in, what will be the quantity n in control surface 2 at time t minus how much is come in from control surface 1 at time t. Now, at time t plus delta t, if I just think about at t plus delta t how the things will happen, this has been changed, the location has been moved. So, what will happen? This will be moved again and this quantity 2 will be moved and it will be seeing that how much of this quantity has moved at t plus delta t from control surface 3 and how much has come in the control surface and the control volume 2 t plus delta t. So, that will be at time t equal to at time equal to t, the quantity n or the system this n, this will be the total change in the quantity which will be coming in. At t plus delta t, how much quantity will be going out, that will be this quantity. So, rate of change of this quantity will be dn upon dt, and if I assume that this delta t is very small, then I can say that delta n upon delta t, this will be equal to delta n will be nothing but n t plus delta t and t plus delta t minus n t upon delta t. I can write it in this way. Now, if I write it, n t plus delta t is what? N t plus delta t is n t 3 okay, into t plus delta t okay, minus it will be n 2 t plus delta t okay. Then this will be this minus again n t at 2 at n t okay. Then again it will be plus n of 1 into t, sorry, this will be n 2 and this will be n 1 t, this will be in this way okay, upon delta t. So, what you can say? You can say that the system final minus initial, I can write it as n 2 t minus n 2 t plus delta t upon delta t, this will be the one. Then I can write it n, sorry, I can write it, this will be again there is something, this is minus, this is plus. Now, this will be plus n 3 t plus delta t upon delta t, which is moving out of the control surface. Now, minus n 1 t upon delta t. These are the three quantities. Now, this is what? This is the control volume quantity, that how much is the quantity is moving out of the control volume in per unit time. So, I can write it out this quantity as dou by dou t of integral control volume integral of the same quantity rho in terms of the intrinsic property, which is eta into dV. Okay. So, this is how much of that quantity, this quantity is moving per unit volume, because section 2 is a control volume. So, I have multiplied it with by the rho, and I have just made it the in quantity and in terms of the eta. So, it means eta is what? Quantity per unit mass. I have multiplied kg per unit volume. So, mass will be cancelled out, it will be as N, capital N, okay, if you write it in this way, and then per unit volume how much is the quantity is changing. So, I can write this whole term is dou by dou t of this term. Now, what about the surface 3? It means how much of the same quantity is going out from the surface 3 and how much of this quantity is coming in from the surface 1. So, we can write it out as how much quantity is going out from the surface separately. So, I can write it out and 3 T plus delta T is equal to that how much is the quantity going out of the surface. It will be nothing but the integral, surface integral, it will be the control surface integral of the quantity which is going out of the system. Now, that will be nothing but the eta, which is the intrinsic property, and the way it has been swept out from that surface. Now, the surface velocity, suppose is v, if v is the velocity of the surface at which the surface is being swept, or it means you can say the velocity of the fluid, then the surface will be swept as a velocity v in the direction normal to the area. So, this will be write as a v dot n, which is the unit vector in the normal direction of the dA. So, that will be the amount of the quantity which will be swept out from the surface 3. Similarly, the similar amount will be swept in from the surface 1 into dA. Similar amount will be swept in from the surface 1. It means the overall change will be written as this minus this can be written as this will be the total swept or total change will be the change at the relative change in the velocity. It means V in minus V out, and I am writing that as a V. So, that will be the V dot N into dA, where this A V is nothing but the change in the velocity, okay, that how much is the velocity of coming swept in and how much mass is being swept out. So, that is the overall total change in the velocity, how it is changing with the time will be written here. So, this whole quantity can be written as dN by dt, dN by dt of the system will be equal to how the quantity is changing with the time, okay, with the time how the quantity is changing in the control volume dou by dou t, okay, plus in the control surface how the quantity is being changed. So, this V dot n is a unit vector into dA. Now, this is called the overall Reynolds transport theorem. Now, any transfer of the quantity can be derived by using this Reynolds transport. So, what we have done? We have done a very simplified approach we have taken. We have taken a moving fluid element in which I have taken an element here. Now, element is moving with the fluid. So, what will happen? Some of the quantity, suppose any quantity, whether it is a mass, whether it is a energy, whether it is a momentum, whether it is angular momentum, any of the quantity will also be swept because of the fluid velocity element. So, what will happen? The swept will be because of the change in the property at the surface, how much it is being swept in from the left surface to the control volume, how much it is being swept from the control volume to the right surface, okay, and that is the total change will be what we will see the effective change in the quantity. So, effective change in the quantity with the time you will see how the quantity is changing within a control volume and how the quantity is changing from the control surface. Okay. Now, if you have a different 6 elements, all the surface element will be changing the quantity and you can have a proper equation that how any quantity is changing with the time from the control surface and from the control volume. So, this is Reynolds transport theorem, and you can derive all your conservation equation by using the Reynolds transport theorem. Okay. So, what we are going to first see that how to derive the mass conservation equation by using the Reynolds transport theorem. Now, for mass conservation equation, what will be my property? My property will be mass. So, n will be what? N will be equal to mass, that is say written by m. So, what will be eta? Eta will be the intrinsic property which will be per unit mass. So, eta will be equal to m upon m. It means we will write it as a 1. So, in the same system, same Reynolds transport equation, I am going to replace the n and eta. So, what is going to be dm upon dt? So, rate of change of mass of the system is equal to dou by dou t of the control volume. Okay. You will write eta will be equal to 1. So, this will be rho of the control volume dv. dv is nothing but the control volume integral, plus you are going to have a control surface, eta will be equal to 1 v dot n into dA. Now, what we can do? We can, this is independent of the time. So, I can put the time inside, the control volume is anywhere we have chosen arbitrary. So, we can write it dou rho upon dou t in the control volume V, and this will be the control surface V dot n is the direction normal to the surface dA. Now, we can use the Gauss divergence theorem. Now, what does theorem do? Theorem changes the control surface integral to the control volume, and if you apply the Gauss divergence theorem here, this quantity will be written as exactly same control volume del rho upon dou t into dv, plus this can be changed to the control volume integral, and it will be written as del dot v, and rho will be also coming in here, the rho will be there. Here the rho will be there. So, this del dot v, or it will be del dot rho v into v. Here we have done this. So, this will be rho will also be here, there will be a rho here. Okay. So, that will be the control volume. So, this will be the control surface here. So, because you are changing in the intrinsic property, here the rho will be there everywhere. So, it will be rho eta v into n. So, that is the whole Reynolds transport theorem. So, here the rho also will come here, and you will see that what is del dot v rho. Now, if you do that, I can write it under both the control volume integral. So, del rho upon del t plus del dot rho v, this will be dv. Now, this is control volume. Because we are using a arbitrary control volume system, we can do that integral. This will be dx dy dz. We will integrate it, it will come as a delta x, delta y, delta z, and we can simplify it as a del rho upon del t plus del dot rho v will be equal to 0, and this is nothing but the mass conservation equation. If the flow is incompressible, then del rho by del t will be 0, rho will come out, and del dot v will come to 0 for incompressible flow. Okay. So, you can derive that how the mass conservation equation can be derived from the Reynolds transport theorem. Again, going back to this eta, how it rho comes, because we are changing the property n to the intrinsic property, and that is why the rho has been multiplied here again. Okay. So, that because you are changing the n to the eta. Okay. That is why I forget here rho, I introduced it, and please be there, and I hope now there will be no confusion why the rho comes here. So, what you have to do, you have to just replace it. If you replace it, you will get and just use the Gauss divergence theorem, which actually changes the surface integral to the control volume integral, Gauss divergence theorem, and it will be nothing but del dot rho v. So, by using that you can derive the mass conservation equation, general mass conservation equation. You can simplify it for the incompressible flow, where del rho by del t will be 0, and then you can write it as del dot v will be equal to 0, because rho will be constant, it will come out, and that you can take it as a 0. So, right hand side. So, you will get the del dot v equal to 0, which is the incompressible mass conservation equation for the incompressible fluid, or velocity continuity equation. So, this can be derived. Similarly, one can derive the momentum equation, Navier-Stokes equation, and for Navier-Stokes equation derivation, what you need to do? You have to take the momentum, it means the system property n will be equal to mv and eta will be equal to v. So, what we will do? We will say dN upon dt, Reynolds transport theorem of the system, will be equal to control volume dou by dou t of the control volume of rho eta dv plus control surface rho eta v, this is eta dot n to d. Now, we will replace it for the momentum, it means this will be d upon dt of mv will be equal to dou upon dou t of integral rho eta is equal to v into dv plus control system rho v into v dot n into d. Now, again what I will do, because this is the control volume, this dou by dou t I can keep it inside. So, I can write it control volume dou by dou t of rho v into dv, where v is nothing but the control volume integral, plus control surface rho v into v dot n to d. Now, again I can put the Gauss divergence theorem, and if I will put the Gauss divergence theorem, this will be control volume dou by dou t of rho v into dv, and this will be again converted to the control volume, and del dot rho v v to dv. Okay. Again the Gauss divergence theorem, the control surface to the control volume. Now, again what we can do, we can say that d upon dt of mv is nothing but this will be equal to control volume integral of dou rho v upon dou t plus del dot rho v v, okay, of the control volume dv. Now, this is the right hand term whatever we have seen here, and this will be nothing but capital dv upon dt, that will be the substantial derivative of the velocity, or you can say that it will be the material derivative. This whole term, the right hand term, we can write it as rho, this term we can write it as rho dv upon dt if rho is constant. Okay. If rho is not constant, we can write it dou rho v upon dou t. Okay. So, what we are going to do, if flow is incompressible, we are going to write it in this way, d rho dv upon dt. Now, what is the left hand side term? Left hand side term, if you will see, I can write it d m upon dt into v plus m dv upon dt, the left hand side term, this term. Now, we know that rate of change of the mass, this will be equal to 0. So, what will happen? You will see m dv upon dt, which is nothing but the force. Okay. So, left hand side term is nothing but the summation of all the forces which is acting on the element, okay, will be equal to whatever the material derivative is, dv upon dt of the control volume integral. So, now on any element, whatever the element we have thought, any element, what are the total forces acting? The total forces acting can be written in terms of the body forces plus the surface forces, Fs plus Fg. Now, let us simplify that what will be the body force, or instead of G I will write it, though let it write FB, which is the body force to the surface force. Okay. So, FB is the body force, Fs is the surface force. Now, what is the body force which will be acting? In absence of any other force, it will be nothing but Fg, which will be the gravitational force which will be acting on the element. Now, what are the surface forces? So, let us assume a simplified case, and I am assuming a cuboid. And let us assume it is being kept inside a moving fluid element. Okay. And this is the direction x, this is the direction y, and this is the direction z. Okay. So, what is the body force acting on this? That Fg will be nothing but it will be rho into g into dx, dy, dz, if this is the dx, dy and dz, a very small element I am choosing, dx, dy, dz, or delta x, delta y, delta z, then this will be equal to actually rho g delta x, delta y, delta z. If dx, dy, dz is very small, infinitesimally small, then we can simply write it in terms of the delta x, delta y, delta z. So, that will be nothing but the body force which will be acting on it, okay, on the element. Now, what are the surface forces? Now, if you see that the surface forces will acting on all the surfaces. Let us assume one surface, the surface which is in the direction of say x. The surface which is in the direction of x, this is dz, this is dy, and this is in the direction of x. Okay. Or I can write it delta x, delta y, and delta z, delta y, and this is in the direction. So, what are the forces which will be acting? One will be acting which will be the normal to this surface, and that force is being given by sigma. So, I will write it as sigma Fx, which is the force acting normal to the surface. Then there will be shear forces will be acting. Now, the shear forces is what? Which is tau, and the tau notation whatever we are going to follow, it is tau is what? It is a second order tensor. What do you mean by second order tensor? It means we need two direction to specify this tensor, and number of component will be what? How many number of component? It will be the number of dimensional space. It means I will write it as, so tau xy is what? It's a second order tensor. It means you require two directions to specify this second order tensor, and the number of element will be equal to how much is the number of space you are using. So, suppose if you are using in 3 dimensional space, so number of space will be 3 and raised to the power n, where n is nothing but order of the tensor. Okay. So, it means if you have a 3 dimensional space, order of tensor is 2, so you will have 9 component of the shear stress. If you have a 2 dimensional domain and order is 2, so you will have 4 component. Okay. So, tau will have 4 component, and the notation which we are going to follow is tau xy. Suppose if I am writing say tau xy, it means what I am talking about? I am talking about this is y momentum in x direction. Okay. It means tau xy will be y direction momentum. It means the velocity will be in the y direction, y directional velocity, it means Vy component, and effect of the Vy component in the x direction. So, that is the way we are going to distribute it. Now, we are talking about in the x direction. So, there will be sigma xx, which is the normal stress component, sigma xx. Okay. Sigma xx will be acting. Now, that in terms of the force, if you have to write, you have to multiply it with the area, and area will be what? Which will be the perpendicular to it. So, in terms of the force, the area perpendicular to the surface, this will be delta y, delta z. Okay. So, that will be the area perpendicular. So, how much it will be? It will be coming into the surface x. Now, there will be the force which will be in the x direction again, which will be effect of the y momentum. So, it will be tau xy which will be acting on it, and tau xy, suppose the direction will be somewhere here, that will be tau xy, say tau xy, and tau zx, the direction will be somewhere here, that will be tau xz actually, which will be the z momentum in the x direction, y momentum in the x direction. These are the forces which will be acting in the x direction. Similarly, the forces will be acting in the y direction, forces will be acting in the z direction, but I am just writing in one directional forces which is in the x direction. So, what I can say? I can say that total force which is acting in the direction of x, that will be written as sigma xx, that will be multiplied by delta y delta z. Then it will be the force which will be acting in the again x direction, which will be the y momentum. So, x into y. Now, that is the force which is the y directional force acting in the x direction. So, what will be the surface which will be acting here? You have to multiply with that surface, and that surface will be what? This is the y momentum force, it will be delta x into delta z. Similarly, it will be tau x z, that will be multiplied by delta y into delta x. Similar, so these are the forces which is acting on the x side of the surface. Similar forces will be acting on the other side. So, this is on this side of the surface, whatever we have said. So, this side of the surface. Similarly, the forces will be the similar forces will be acting on this side. So, total net change in the x direction force will be, you have to just subtract it. If you will subtract it, you will write it as sigma xx minus at say x minus sigma xx at x plus delta x. Okay. You multiply it by delta y delta z. The total forces, surface forces, I am adding it. It will be tau x y at surface y minus tau x y at surface y plus delta y. This will be multiplied by delta x delta z plus tau x z at x z minus tau x z at z plus delta z upon multiply by delta y delta x. Okay. Plus that is the total force. So, total force, this is the surface forces plus the body force. Body force is nothing but the Fg. Fg can be written as we have defined, it is nothing but Fg is nothing but rho into g delta x delta y delta z. Now, you can divide it by delta y delta z delta x delta z, that will be the F, and you just divide it by the delta x delta y delta z. This will be nothing but, you can write it sigma x x minus sigma x x, this is at x, this is at x plus delta x upon delta x plus tau x y at y minus tau x y at y plus delta y upon delta y plus tau x z at z minus tau x z at z plus delta z upon delta z plus rho g. So, you can write it as by using, if delta x, delta y, delta z are very small, infinitesimally small, you can write it in terms of the differential equation. We can write as d sigma xx, I will write it in terms of the dou upon dou x minus dou tau xy upon dou y minus dou tau x z upon dou z plus rho g. Okay. So, whole minus will come out, it will be dou sigma xx upon dou x plus dou tau xy upon dou y plus dou tau zz upon dou z. Now, because we are writing it in terms of the x direction, gravity also I will write it in the x direction, and instead of g I will write it as a rho gx. So, what we have done? Total force which is acting in the x direction. Similarly, one can write it in for the y direction, for the z direction, and that will be the total summation of the force, and that is the force which we are writing is integral control volume of d of v upon dt. I am writing it for incompressible flow of dou v. Okay. Now, this divided by the total volume, there the total volume has been divided. Now, if you do that here, delta v, delta x y this is delta x, delta y, delta z is here, and that you are writing as minus of dou sigma xx upon dou x plus dou tau xy upon dou y plus dou tau zz upon dou z plus rho gx. Now, if you do that, if this is infinitesimally small, dv can be written as dx dy dz. If you integrate it, it will be delta x, delta y, delta z. That can be cancelled out, and you can write it as rho dv upon dt is equal to minus of dou sigma xx upon dou x plus dou tau xy upon dou y plus dou tau zz upon dou z plus rho gx. Now, the normal stress term, we know that the normal stress is the combination of the pressure plus the stress in the normal direction. So, I can write it as minus sigma pli plus tau xx, okay, upon dou x plus tau xy upon dou y plus dou tau zz, tau xz, sorry, not zz, this is xz everywhere, sorry for this, tau xz upon dou z plus rho gx. So, you can write it as rho dv upon dt will be equal to minus dou p upon dou x minus dou tau xx upon dou x plus dou tau x y upon dou y plus dou tau xz upon dou z plus rho gx, and this term can be written as minus dou p upon dou x minus del dot tau plus rho gx, and this is the x component of the tau. So, this is rho dv upon dt. Now, the whole Navier-Stokes equation can be written as dou dv upon dt minus dou p minus del dot tau plus rho g, and this is nothing but is the momentum equation. Now, if we write it in terms of mu also constant, then this whole equation can be written as rho dv upon dt will be minus dou p plus mu del 2v, because tau is equal to nothing but minus mu dou v. So, del 2v plus rho g, and this is called Navier-Stokes equation. So, this has been derived from the RTT by doing the property balance, and property is nothing but the momentum. So, that is the general equation which is called momentum equation or general momentum equation, and from momentum equation, if you assume rho is constant, mu is constant, you can come to the Navier-Stokes equation, okay, which will be in this form. So, this is the 3-dimensional Navier-Stokes equation has been derived from the basic Reynolds transport theory by assuming a control volume in which some property, and the property is momentum, which is coming in, which is being there and then is going out from a control volume. So, how much property is coming into the control volume, how much property is going outside of the control volume, the net change is this, the written it in this form. Now, we are going to use this equation in terms of, now this is dv by dt, again if you open this dv by dt, that will go in terms of the Eulerian as well as the Lagrangian measurement variables. Now, what we are going to do? We are going to use this equation, we are going to see that how the equation will be modified in case of multi-phase flow. But before doing that, what I am going to do? I am going to simplify the equation in the one-dimensional form. This is the 3-dimensional equation. If you want, you can get the solution for this, but you again need a numerical approach or computational fluid dynamics method to solve this equation in the 3-dimensional domain. Now, what I am going to do? I am going to simplify the equation in the one-dimensional form. Now, if I have to simplify the equation in the one-dimensional form, what I am going to do? This rho dv by dt will be equal to minus dou p by dou x minus, I will write first in terms of the tau. So, this will be dou say tau upon dou x, I am writing it in the one dimensional plus rho g. Okay. Let us assume that this is the my equation. Now, what I am going to do? I am writing it in terms of the one dimensional, again I am going to write it in terms of one dimensional. So, say in the direction of x I am writing, so dou v x into dvx upon dt or dx, okay, assuming that the flow is steady state, Vx upon Vt term I am neglecting the steady state term. So, steady state flow. So, if the flow is steady state, it means dou Vx upon dou t term I am neglecting. This is the one dimension. So, rho dou Vx upon dou x will be equal to minus dou p upon dou x minus dou tau upon dou x plus rho g x. Okay. I am writing it in x direction. Okay. Now, what I am going to do? I am going to multiply with the area, which is the cross sectional area everywhere. I can do that into A. Now, if I do that area multiplication, this is what? This is nothing but the mass flow rate, and I am going to denote it with m naught. Okay. So, this is how much of the solid is flowing in the x, how much the fluid is flowing in the x direction. So, m naught dvx upon dx area into dou p upon dou x minus now area to gx. Now, A into dx, if I try to reduce it, it will be in terms of the perimeter. If I am assuming that this x is very small element and I am just doing the changes in a very small element, I can just cancel it out. I can write it minus A dou p upon dou x minus area upon dx, it will be perimeter, which is p into dou tau A gx. Okay. So, equal to m naught into dvx upon dx. Many books is write in terms of the g in a standard multi-phase flow books. This some book also write it in terms of the g. So, do not get confused if you see the g symbol, it is just nothing but rho v into x. Now, we can simplify it what we want. Again I am going to write it in terms of the dou p by dou x, because that is what we want to calculate. So, I will write it as minus m naught into dvx upon dx divided by area. This will be minus p upon a into d tau plus rho into gx. So, that will be what is the total pressure drop you are going to see, and that total pressure drop is going to be the function of all this. Okay. Now, what if you will see here, okay, what we are going to do? We are going to say this is as dou p by dx, and because the pressure drop is going to take place, it is going to be negative. And instead of writing final minus initial, I am going to write initial minus final. It means everywhere I will take the minus sign out. So, this will be dvx upon dx plus p upon a d tau minus rho gx. Okay. Because this p is now initial minus final, instead of final minus initial, initial minus final. So, it will be in this form, we can write it. Now, if we will write it in this form, what we can say that the total delta p across the pipeline in the single phase flow is going to be the function of three things. One is the frictional parameter, second one is the acceleration field because of the acceleration, because of the frictional, and because of the gravitational. So, dp by dx can be written as m naught upon a into dvx upon dx plus p upon a tau w minus rho g x. So, this is acceleration, this is due to friction or viscous forces, and this is due to gravitational forces or gravity forces. So, the dp by dx in any pipeline is function of these three things, whatever we have discussed for the pneumatic conveying in the previous classes. that this is the function of acceleration, fluid acceleration, it is the function of the friction of the fluid, it is the function of the gravity. Now, if you have a multi-phase flow, what you are going to have? This is the phase 1, you will have the delta P, because the overall delta P in a pipeline because of the acceleration of one phase, acceleration of another phase or second phase, friction because of the phase 1, friction because of phase 2, gravity force because of phase 1, gravity force because of phase 2. In single phase flow, this is going to be the function of this. So, I can say dP upon dx of frictional component is written as P upon A tau w. Okay. Now, d tau w you can write, or tau w you can write if the change is very small, and P upon A in a cylindrical pipe, if you are thinking about, then the perimeter is nothing but pi by d, area is pi by 4 d square to tau w, or you can write it equal to 4 tau w upon d in single direction, one dimensional. Then dP upon dx due to acceleration is nothing but m naught upon A into dvx upon dx, that is the Lagrangian acceleration term, how it is changing with the velocity is changing with the position x. Okay. Then dP upon dx, which is the gravitational forces, is equal to rho g x. So, this is the combination of all these three. Now, even in the single phase flow, if you want to find the pressure drop, the problem is it is forced to measure the Lagrangian velocity. You should know how the v is changing with the x. Second and most important is how the tau is being defined, and the tau is being defined, tau w is defined in terms of the fanning friction factor, it is F rho u square by 2, where F is fanning friction factor. And we know that finding the fanning friction factor itself is a difficult job, and you have to go to the Moody chart or some correlation which is being developed, empirically developed correlation to find the F value. For laminar flow, it is relatively simpler. So, if the flow is laminar, F is nothing but 16 by Re, and if flow is turbulent, then what you need to do, there are several empirical based equation, you have to either use that or you have to use the Moody chart, okay, and where the F is being plotted with the Reynolds number. This is for the laminar flow and this is for the different turbulent flow, and this is for different K upon D, where K is nothing but the roughness factor coefficient or roughness value. This K upon D is called roughness coefficient and K is roughness. Okay. So, the simplest equation for the turbulent flow where the pipe is smooth is equal to, it is 0.625 upon Re raised to the power 0.25. Okay. This is the way F has been defined. If the roughness is plays the role, there is different correlation, Colebrook correlation is there. Which can be used to find that what will be the value of this friction factor, and the one form of the Colebrook correlation for the fanning friction term is 1 upon under root F is equal to -4 log of twice K upon D plus 9.35 upon Re under root F plus 3.48. This is the one form of the Colebrook correlation. There are different Colebrook correlations available, form of this correlation available, which is valid for the different Reynolds number. There are other correlations also available to find the F values. So, what I am trying to say that even for the single phase flow, calculating the delta P is a challenge, and that is mainly because of the acceleration term and because of the frictional term. And the frictional term, the problem comes with the friction factor value, that how to calculate the suitable friction factor value for the one dimensional flow in a single phase flow, and different correlations are available. If the flow is laminar, finding the values is relatively simpler because you have a straightforward correlation f equal to 16 upon Re. If the flow is turbulent, then if there is a roughness parameter, then the solution becomes iterative, and if you see that if you have to solve this equation, then you have to do the iteration to find the value of f for the different Reynolds number, or for the same Reynolds number how the value of f will change. You have to do the iterative solution to get the f value, or you have to move to the Moody chart. You have to see that how with the Reynolds number f is changing and what is your roughness parameter, and depending upon the roughness value you can find the k upon d. For a particular k upon d, for a particular Reynolds number, you can find the f value. So, it is still a challenge in doing in the single phase flow. The challenges will get double, will increase at least, if I will not double I will say, once the multi-phase flow comes into the picture. Why? Because now the problem is even to find that what is the area. So, first you have to find what is the area, what is the velocity inside of the fluid, because now it is not filled with the single phase, it is filled with both the phases available. A particular fraction in the pipeline is being occupied by that particular phase. You have to find that fraction, you have to calculate the velocity inside, you have to calculate the Reynolds number inside, and based on that Reynolds number you have to calculate the f value, and then you can calculate the delta p in the pipeline. So, what we are going to do from the next class is we are going to use the regimes. First I will focus on the gas liquid flow. We will take the different regime, homogeneous regime, separated regime, annular regime, all those regimes we will take. We will see how these equations need to be modified in those regimes to calculate the delta p. We will also try to see some of the empirically developed correlation like Locard-Martellini correlation, which is widely used in all the industries to find the delta p in a pipeline. So, we will understand those systems and we will see that in each regimes how the equation will get modified, what are the challenges we have to see in the each regime, and then we will try to do some assignment problem on each regimes to understand, to have more clarity on it.